Hi, welcome to another edition of Calculus 3. Today we are going to talk about chain rules for functions of several variables and implicit differentiation. Let's go ahead, take a look at this very useful topic. So, as usual, we are going to go back to Calculus 1, refresh our memory about what the story was there, and then we come to a multivariable case and continue the story from there. So remember, in Calculus 1 you came across the following situation quite often. You have a variable x that determines some intermediate variable u, which then determines a third variable. Let's call that w. So I can have u as some function of x and w as some function of u. Let's go ahead, write down some examples. So we are talking about something specific. So suppose u is, say, x squared, and say w is, say, u cubed. Now when we have a chain of variables in this fashion, and when you change the first one, of course the next one is going to change, and that change in that is going to get magnified and change the final item. We typically want to know a direct expression that connects the change in the first one to the change in the last one. You can think about it as a sensitivity analysis or just derivative and so on. Well, there are two ways of going about it. One is a direct substitution and finding out how w depends on x. And the other one would be using the chain rule. So what's a direct substitution? So direct substitution, as the name implies, direct substitution, well, you can replace it by x squared in this case. So w was u cubed, u itself was x squared, which is now being cubed. So obviously w is x to the power of 6. If you want to know how w depends on x, or sensitivity of w to x, you simply differentiate. Let's write in Leibniz notation so it's clear as to what we are doing. W is changing with respect to x, and the derivative of it, you simply obtain it as 6x to the power of 5. Well, if a unit of change in x causes certain change in u, and the change in u causes certain change in w, then the change in x causes a change in w. And how does that go? The rate of change of w with respect to x by chain rule, so here's a chain rule, is the rate of change of w with respect to u times the rate of change of u with respect to x. So dw du, that's easy to find. Dw du, straight calculation, 3u squared. Du dx, on the other hand, du dx, the derivative of u with respect to x, is 2x. So the chain rule simply multiplies these two, and I have 3u squared here times 2x there. And when I multiply, well, of course I get 6u squared x. How is it that once we are getting 6u squared x for dw dx, and here we are getting 6x5? Well, if you look at this, you notice that this is the same as that. You remember u was x squared, so this is really 6, u was x squared, that's being squared, times x. So this is also 6x5, same as over there. So the chain rule is a very important rule in calculus. You use that pretty much in every differentiation problem. Hard to avoid it. It is all over the place. Now, the same degree of importance applies in higher dimensions. When you have more variables, same kind of an idea applies. So in this case, we have a function w of x and y. Now x and y themselves could depend on another variable. Let's start with a very simple case where x and y depend on just one variable. So for example, we can say x is some function g of t, or x of t, and y is some other function, let's call it h of t. So a very good way to negotiate in this alphabet soup is to draw a tree diagram for dependency of our variables. So in this kind of trees, typically the root is at the very top, so it's kind of strange in that way. W depends on x and y. So next level, the dependency of W is on x and y, and x and y themselves depend on another variable. Here we draw some lines to indicate that at the next level these two depend on t. Now if I change t, x and y will change, and as a result W is going to change. What we wanted to find out is the sensitivity of W to t. That is, if I change t by a small amount, how much would W change? Well, that's essentially what the chain rule in higher dimension is. So what we need to know, let me go ahead and write down what the expression is, and then we'll explain it shortly based on the concept of differentials. The way W depends on x and y is through its partial derivatives, partial of W to x, or del W del x, partial of W with respect to y. These two quantities measure how W change when either of these two changes. Now x has just one dependency, that's just t, so instead of using the partial notation we use the ordinary derivative notation, so dx dt. We could have used that too, but here it is more common to use this notation, dx dt and dy dt, because there is no other variable competing with t for this dependence. Now when I want to find out the rate of change of W with respect to t, I start at letter t and go all the way to the root and multiply all these dependencies just the way multiplication happened here. We do the same multiplication, except that there are two paths starting from variable t to variable W. So rate of change of W with respect to t is rate of change of W with respect to x, which is a partial of W with respect to x, times derivative of x with respect to t, and whatever contribution we have from other competing path here, so partial of W with respect to y times the derivative of y with respect to t. Let's go ahead and apply this in a simple case so that it's clear what is meant by it, and then we come back and give a bit of an explanation here. This is essentially that total differential formula that we had in the previous section. So let's take a simple function. W is, say, x squared plus say xy and then say y cubed. And to keep the problem simple, let's make the next level g and h to be very simple functions so that we don't get bogged down with too much algebra here. So y is, let me remind you, this is our function g here, and say y is t cubed, and that one we named it h. So in this problem it is easy enough for us to do direct substitution, that is, pick these definition of x and y, plug it here, then we'll have W in terms of t, and we can differentiate. So just as in the 1D case, let's go ahead show what is it that we are after. So if you want to do direct substitution, if that was possible for us to do, well, in this case it is W, instead of x I have t squared and then squared, and then x is t squared and y is t cubed, and y was t cubed and itself is being cubed. So to simplify, this is t to the 4 plus t to the 5 plus t to the 9. Well, now we have direct dependence of w on t. We have gotten rid of the middleman x and y. We know directly how does w depend on t. Well, now you can differentiate if you want. This is dw dt. Simple problem from calculus 1. 4t cubed, 5t4, 9t8, and you're all done. Now, applying chain rules. What does it mean? Chain rule. So we have dx dt, of course dx dt is 2t, just like before. Dy dt, derivative of this thing, obviously 3t squared. Now we have to multiply each of these things with the partial of w with respect to x. So what is the partial of w with respect to x? Maybe I pause for a second and ask everybody to try to finish the problem by themselves. So here you remember that our cue was that when you see this picture, you try to do the problem by yourself and not wait for me to do it. So you do it and then come back and compare. So as much of it as you can, you do by yourself, and then pause and come back and check and go alongside with me. So w dx is going to be the derivative of this is 2x, and then plus what? Derivative of this with respect to x, of course, that is y. Let's go ahead and do the other one also. dw dy, derivative with respect to y. What is that? Well, this is 0. Here, derivative with respect to y is x, and then 3y squared. So if you want to write it in terms of the function t's, this is going to be 2t squared plus t cubed, and this one is going to be t squared plus 3t cubed squared, which is t squared plus 3t6. So with the chain rule, if I want to calculate dw dt, what I have is that this derivative has to multiply this derivative, so I have to have 2t. Let's remind ourselves what these things are. This is dx dt, then partial of w with respect to x, which is this one, 2t squared plus t cubed, plus partial of y with respect to t, that would be partial of y with respect to t, that was 3t squared, times, let me clean this up and restate what I said. I misspoke. So this was derivative of y with respect to t, and this is a partial of w with respect to y. Partial of w with respect to y was t squared plus 3t6. So just multiply it out. So it's 4t cubed plus 2t4, and then another 3t4 plus 9t8. So of course when we clean them up, so 4t cubed, these two combine, 5t4, 9t8, which you notice these are the same thing. So that's the idea of a chain rule in a multivariable case. Let's see, where does it come from? You remember we had the idea of a differential. If w is a function of x and y, if I make a change in x and a change in y, I want to figure out what's a change in w. Remember the total differential was f sub x dx, and the partial of f with respect to y times dy. Remember we had a demo that we were looking at the tangent plane to the graph of f of x and y, and in the x direction we were traveling by dx, in the y direction we were traveling by dy. We wanted to find the increment in w. We approximated via the differential dw, and this expression came there, essentially showing how the tangent plane looks like. And if you compare this thing with the formula that you have here, you see we are looking at w, x, and y as functions of t, and we are writing the derivatives of these functions with respect to t. So this formula is essentially same as the total differential formula that we had before. Same thing happens if you have more than two independent variables, essentially same idea. So let's just write the general formula. If I had w as a function of, say now we throw in a few more variables, say z as well, then if x, y, z, all of them depend on some variable t, then the rate of change of w with respect to t would be, now let's abbreviate this thing, the derivative of f with respect to x, partial derivative of f with respect to x, we had this shorthand for it, then times dx dt, and then fy dy dt, and then fz dz dt. Sometimes, to abbreviate further, the name of the function is taken to be same as the name of the output of the function. So sometimes this is written like this: w is a function, just to remember that the function as output w, we name the function also w, and then we have the following look for this. We have dw dt. Now here will be wx dx dt, wy, so that means partial of this function with respect to y dy dt, and partial of w with respect to z dz dt. This is a cleaner notation than this because we are saving one more name and reducing the number of names we have in our formula. Sometimes it causes confusion as to what is meant by this. wx, w is the name of the function, and you're taking partial derivative of that particular function. Okay, so this is one type of chain rule we have, and there are some other types as well. Sometimes we have this variable w that depends on two variables x and y, and then in turns x and y themselves might depend on several variables. So in the previous case here, x and y just depended on one variable t, but it's possible that we have a more crowded situation that x depends on t and say s, and y also depends on t and s. So we have a cascade of variables. At the root we have w depending on next level of variables, and these in turn could depend on the next level. You can imagine you can have more branches on this. So the idea is the following: if I change t and s, then they are going to influence x and y, which in turn are going to influence w. So changing t is going to change w. Now there are two ways of influencing w. If I change t, an influence goes up this stream and reaches w, and another influence goes up this stream and goes to w. Here let's indicate that if I focus on just t, if I change t, t influences x, and then x influences w. However, on this path also y is going to change, and once y changes, then w is going to change as well. So let's for a moment assume that we are holding s constant, just not to crowd the situation. Let's suppose s is kept fixed, and then we want to see how does W change when T changes. Due to the fact that there is a competition for T, we have to use the partial notation. We have to say what is the rate of change of W with respect to T. We have to use the partial notation to distinguish between T and S. If there was just one variable here to worry about, we could have said dW dt, but when there are several competing variables, we have to use the partial differentiation to distinguish between them. Okay, how does it go? Exactly like before. You have to follow the chain rule on each of these paths and simply add them together. So this becomes partial of W with respect to X times partial of X with respect to T. That follows the trajectory here. We have a second trajectory, and the contribution from that is going to add to the first one. So partial of W with respect to Y, and 10 times partial of Y with respect to T again. Notice that in this kind of notation, we did not use a different function name, like we moved away from using different function name than the output of the function, and we are using this more abbreviated notation to make our formulas utilize less letters and be less cluttered. So we just have the name of the variable, and the function is also named by that variable. Now you go ahead and tell me what is the rate of change of W with respect to S. Okay, so you want to pause this thing for a second and write for me what that thing is. So here's our signal for pausing. You want to write for me what is partial of W with respect to S. Let's color it different, so I change S and X changes, and also Y change. Now in this next level, it is the same as what we had before. You want to draw it red or blue, it doesn't make any difference, but just to indicate we have a continuous path here. From S to W, we have two paths. On each of these paths, we multiply the sensitivities going up and then add them up. So we have partial of W with respect to X, then partial of X with respect to what now? It's S. Partial of W with respect to Y times partial of Y with respect to S. Now if you have taken your linear algebra class, you can write this crowded looking situation using matrix notation, make it a bit more abbreviated perhaps, but for the time being we just leave it in the form that you see here. Of course, if I had X, Y, Z, and down here I had R, S, T, and so on, so my tree is going to be more crowded. So if I had something like this, X, Y, Z, and then perhaps these things could depend on 2 or 3 or 4. Each level we could have a different number of dependencies, but just to here, so your tree can become quite RST, maybe RST, RST. Now your formulas become much longer, but the idea is all the same. Okay, now there was one topic showing up toward the middle of Calculus 1 called implicit differentiation. Let's go ahead, review that, and then see how does that work in higher dimension. Implicit differentiation, suppose you have a relationship between two variables, but the relationship is not easily expressible in terms of one of them. So suppose we have something like, say, x squared plus, say, xy and, say, y cubed, say equal to 5. This one obviously connects x and y to each other, but it's not an implicit function because we don't directly have y in terms of x. When we get lucky, we can actually go ahead and find it, but more often than not, we don't have it, or it might be very hard to find. So in those cases, if you want to go ahead and find the derivative without spending the effort of finding the function in an explicit fashion, so what do we do? So suppose the question is, what is the derivative? So we want to find the derivative, but we don't have y in terms of x. Well, the next best thing is to go ahead and differentiate and get a derivative. The cost we are going to pay is that the derivative also going to be implicit. So let's go ahead and differentiate with respect to x. This is obviously 2x with respect to x. Derivative of this with respect to x. Well, of course, we have to apply the product rule. Derivative first is 1 times y plus x times the derivative of y with respect to x. Derivative of y with respect to x, well, commonly we write it as y prime or dy dx. I write y prime so that it is shorter. Derivative of y cubed with respect to x. Do you remember what that is? Maybe you want to pause for a second and tell me what is the derivative of y cubed with respect to x. Is this what the derivative is? You want to pause for a second and be sure of that. No, that's not all of it. You have to still multiply with derivative of y with respect to x. If you are wondering why you didn't do it here, well, derivative of x with respect to x is 1. You don't need to write multiplication by 1, but derivative of y with respect to x, we don't know what it is and we need to include it. In this case, right hand side is just a constant and its derivative is 0. What did you do in calculus 1? We said, well, you want to find this derivative. This is what you are after, isn't that? So this is what you want, y prime. So you go ahead and factor it, y prime times x plus 3y squared. So this is the y prime that we are after. Now these other terms go to the right hand side, so I'll have minus all of this thing, 2x plus y. So easily y prime is obtained, minus 2x plus y over x plus 3y squared. So very different kind of situation than what you had at the very beginning of calculus 1, where the derivative of y with respect to x is given as a function of x. Now we have an implicit function because y itself has to be found out from here and then plugged in this formula to get your dependency for y prime in terms of x. Typically y in terms of x might not be easy to find, so we just leave this thing as it is. Okay, this is how implicit differentiation was done in calculus 1 again. So this is a review from calculus 1. Well, what is news here? News here is that we have another way of finding this, which is also generalizable to functions of more variables. The way we do this thing is we say let's define a function of x and y, which is the difference of the two sides of this equation that you have here. So I have w, I bring one side to the other side, so x squared plus xy plus y cubed minus 5. If I set w equal to 0, I'm restricting myself to this relationship. Okay, when w is 0, I am right at that relationship between x and y. Okay, you remember our total differential formula. Total differential formula was dw was w with respect to x dx plus dw with respect to y dy. That was the total differential. Now, if W is a constant, in particular if W is equal to 0, which it is when this is equal to 5, if W is a constant, its change, its total differential will be 0. So this one, I write this thing, in that case this is 0. So in that case I will have Wx dx plus Wy dy is equal to 0. Now I can write this thing as Wy dy is equal to minus Wx dx. Cross multiplying, I will have dy dx is equal to minus Wx over Wy. So what's Wx and Wy? These are partials. Wx, derivative or partial of this with respect to x, that is just 2x plus y. And Wy, that's going to be x plus 3y squared. So what is this quantity? This is saying minus Wx, which is 2x plus y, and then this one is x plus 3y squared. Do you see that this is same as that? So instead of the approach that you had in calculus 1 to find the implicit derivative, we have another method which is kind of cleaner, faster, and cuter than that one, and it gives us, well, it should give exactly same answer. The nice thing is that this idea is applicable in any number of variables. Doesn't have to be just an x and a y. So let's go ahead for our final example. Let's throw in one more variable in the mix. Suppose I have a surface indicated by, say, x cubed plus, say, 3xyz plus 2z, say, squared is equal to 5. And say I want to find out what is partial of y with respect to x, perhaps at a specific location. We want to find out this partial. Okay, let's pause for a second, make sure we are not drowning ourselves in letters and such. Make sure we understand really what is it that we're talking about. So let's go ahead to that nice software that we have, see if we can make use of it. First of all, what is this thing? I have x, y, z mixed into some formula equal to some number. That is, of course, a surface. But due to the complication of the formula, we have a hard time figuring out what it is. So let's just assure ourselves that, okay. So I hope I have typed this thing correctly here. This is x cubed plus 3xyz plus 2z squared. And I brought the 5 to one side. Here we have bring everything to one side in the software, and just type it and press return, and we get some surface. Rather hard to figure out what it is. It's like a advanced chips, if you wish to look at it that way. Quite a few turns and curves in it. Okay, now we were asking for partial of y with respect to x. What does that mean? It means we are holding z as some constant. So in this curve, on this picture, I can throw in a slice at a fixed z. For example, z equal to 2 or any number. So here, so this surface that you see reflects z equal to 2. The original, well, is that strange looking chips, you wish to think about it that way. Well, they are going to cut each other. There's going to be a slice. That slice is some curve. Okay, so when you have a bunch of more than two variables, a bunch of variables, you're holding all but two of them fixed. So here we are holding z fixed, and we are just investigating how do x and y depend on each other. So x and y are now sitting on this the position of the slice, so either here or it could be on this branch here. Okay, when we are asking partial of y with respect to x, what are we after? We are after the slope of this curve. Okay, we have a very hard time with that, what the surface is, and then in addition to that, there is a cutting plane. On that cutting plane we see a curve, and we are going for the slope of that curve. How can we do that? Visually it's a simple idea. As far as algebra is concerned, it's a bit convoluted. So what do we do here? It's very similar to what we did in the previous case. If you want to find the partial of one variable with respect to another variable, you first of all define another variable, which is the difference of the two sides of this equation that you have. So say w is equal to x cubed plus say 3xyz plus 2z squared minus 5. So w equal to 0 is same as that surface we were looking at. Now partial of y with respect to x, exactly like here, there's a minus minus partial of w. Let's write it this way so that it fits easily. So it's going to be partial of w with respect to x over w with respect to y. Notice that the positions are crossed. So in this case it's going to be minus of derivative or partial derivative of w with respect to x. That's going to be, for example, here 3x squared plus 3yz, and partial of this thing with respect to y is 3xz, and here with respect to y I don't have anything. With respect to y I don't have anything here either, so that's all there is to it. Don't forget this presence of this minus. Where does this come from? Again, same as idea of total differential. If I have this function of w of x, y, z, if I want to write the total differential of w, it would be partial of w with respect to x, differential of x, partial of w with respect to y, differential of y, plus partial of w with respect to z, differential of z. Okay, we are now say let's w be fixed. Why w to be fixed? Because we want to be on that surface. If w is fixed, then dw will be 0. Moreover, you are holding z also fixed, so this also is fixed. So let me show you again. Okay, so when you are slicing it with some z equal to some number, that is same as saying z doesn't change, which means dz is 0. Okay, and when you say w is 0, it means you are right on the surface. So two items are out, and two items are staying. To signify the fact that we are holding z fixed, we are going to use the partial notation here instead of the differential that we had over there. So here we are going to have setting this equal to 0. If you wish to write it like this, wx partial of x, wy partial of y is equal to 0. So these two are both gone. And partial of y with respect to x becomes, so you take this thing to the other side, that's where the negative comes in, and then you have partial of x with respect to x and w with respect to y, and you get your answer. Same way you can apply, you can hold any of these variables as fixed quantity, so its differential becomes 0, and play with the other ones left. In this notation, you remember that you always are considering the rate of change of one with respect to other, while all others are held constant. Okay, so we covered chain rule and also the implicit differentiation, and you want to look out for several exercises related to this. There's plenty of this kind of relationship when you come to your heat transfer classes. They have all sorts of concepts of energy and pressure, temperature, volume, and so on, and relationship between them when some of them are held constant, some others are variable, and so on. So there's going to be a lot of application of this in your thermal class. Okay, until then, good luck and God bless.